Today's a wonderful day. We're going to be transitioning. We've been really good at talking about what's happening when we think about rates of change. We really start at the ground level, saying, okay, how do we understand things? Well, we have this average rate of change, we build up, and now we've gone, wow, really great at it. So now that we've answered the question, okay, what's happening with how things are changing? Today we're going to move to a new question. What's the total? Now, it feels interesting to say, why are these two seemingly different questions being raised in the same course? Well, there's a good reason for that, which we'll talk about in a future session. But for now, let's begin. So, as a quick reminder, we have this idea, differential calculus. The main question, how are things changing? And how did we do it? So if you go back, the idea was you had a curve, and of course it could be doing all sorts of crazy bumps, but then you said, all right, if I want to understand the behavior at a particular place, no problem. So if I wanted to understand the behavior here, well, what was the idea? Idea was you zoomed in, and if you zoomed in really close, what would happen is that lo and behold, things would look more flat. And then, of course, you could zoom in again, and it would become super flat. And then that was our sort of our build-up to talking about rates of change. Things look like a line. Life is good. Now, we're going to transition to a new topic. Still part of calculus, but it's not interested in saying how are things changing. It's interested in the question, how much is there? And before we get too far into it, we're going to focus on sort of one interpretation, but we have to be careful. So we're going to start our understanding with saying, well, how much area is there? Now I'm putting area in quotes for two reasons, and two very important reasons. The first reason is we'll allow for negative area. Of course, that seems somewhat strange. You can think of it as maybe signed area, where we say, okay, area could be positive or negative. You can contribute to the total. You can remove from the total. But the second reason is really, really important, and I want to make sure we say this at the beginning. When we're talking about the total, we don't only have to talk about total area. We can talk about totals of anything. We can talk about total volume, we can talk about total mass, we can talk about total money, right? We can talk about total time. Anytime there's a question that can be phrased as, well, what's the total? That's a question that we can put into integral calculus and ask for the tools. So, we have our question. How do we approach it? For us, when we talked about differential calculus, it was like, oh, zoom in, zoom in, zoom in, and it becomes flat. So we have to think, okay, how do we go about finding our total? Well, if we're after, say, this area that's been shaded, so we have some curve here, our function, f of x, going from a to b, what we can do is say, all right, the curve is hard to understand, but let's think about something that's easy to understand. Now for area, the easiest thing for area is a rectangle. We understand rectangles really well, and for us, we think of rectangles as the flat thing. So we say, aha, rectangles are flat. And so what we'll do is we'll take our function from a to b, break it up, and approximate it by a bunch of rectangles. And you see that these rectangles here have been chosen so that they roughly match the height of what the function is in each little piece. And if you look, you say, wow, look, it's not a bad estimate, right? Because you see, it's a reasonable approximation to what the function is doing, but not perfect. You see, there are some places where it overshoots the function to the rest of the rectangle, and some places where it undershoots. So what you see is there's these gaps here. And these gaps are, in some sense, they're like our errors. And it says, okay, look, your approximation isn't perfect. There's little amounts of error there. So, all right, we have this nice idea, flat things. What's our zoom in? Our zoom in says, hey, if we want a better approximation, make our rectangles thinner. Then what happens is that the errors become small, almost imperceptible. to the point where it's really even hard to shade them because they're so tiny, these errors. And now our errors are getting smaller and smaller, which means our answer is becoming more and more accurate. So as we continue, smaller rectangles, smaller rectangles, smaller rectangles, we're going to get better and better approximations. And if we're very patient, we make the rectangles as small as possible, whatever that means. We'll have the answer to what's the area, which really is the answer to how much is there. Now there's a process for this, and it goes by the title, Riemann sums. All right, so if you're from Iowa State, not to be confused with Riemann Gardens. No, different, completely different. All right, Riemann sums. Well, what is that? So what we want to do is, again, we have a function, and we want to approximate the area under the curve from A to B. So we have our function, f of x, and here's our function, here's A, here's B, and we want to approximate the area underneath. So how do we go about doing it? Well, the basic idea is to really just do what we talked about, right? Which says, okay, we're going to split up the interval from A to B. So we're going to think, okay, starting at A, go to B, and chop that up, boop, 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 and chop up into some number of pieces. Okay, now there's no constraint that says, oh, the sizes have to be the same. So you could have some which are bigger and some which are smaller. Generally speaking, we make them equally sized. Now, the important thing is for the approximation to get good, they should all be getting small. They don't all have to be getting small at the same rate, but they should all get small. So it's like, okay, so we're splitting up downstairs into some number of slices. Okay, that's what we say here. And now it says, all right, look, at some interval, so you have some a sub I minus 1, a sub I. So these subscripts are indexes, just to keep track of which point is where. We say, look, there's got to be a rectangle that we represent. Now, the width of the rectangle, that's our width of our ith piece. A sub I minus a sub I minus 1. In other words, it's how far across it is between. And then the height, well, what it is you go up to the function. Now, here is where, of course, it gets interesting, because it could have been chosen in different ways, depending upon where you choose it. So you may have said, oh, if I choose it here versus if I choose it there, you'll say, oh, wait, the heights are different. Yeah, the heights are different. Absolutely true. The heights are different, depending upon which point you choose. But now, here's the important idea. Here's the magic that makes everything work. While it's true that the heights will vary, when we're close together, so in other words, that a sub I minus a sub I minus 1 is very small, the height upstairs will not vary by very much, which says, okay, yeah, you might have a little bit of perturbation, but not very much, very small, and that's why it's a good approximation. So, okay, you have a width, you have a height, so multiply them together, so it's the function somewhere in the interval times the length of the interval is the area of the rectangle. All right, great. Of course, that's one little piece, and now you add them all together. So when we're talking about Riemann sums, it's really saying we're after a total. Usually we think of it in terms of area. We split things up into little parts, add the contribution from each little part together, if we think about it as a rectangle, and then we have the answer for at least an estimation, that is to say, of what it is that we're looking for. All right, well, so here is a nice example where we start A0. Well, we're thinking of A0 as our A, our starting point, and A6, that's our last one, that's our B. And now the key thing that people often say is, how do you pick? Because you could have had lots of choices. How do you pick? And the answer is, you pick however you want to pick. There's not a correct way, but sometimes they'll specify. So what are some common things you see? Well, you might see a left endpoint. Well, that says, suppose I have an interval the left endpoint would be on the left-hand side. So that would say, okay, choose whatever the height is at the left end, that's the height of your rectangle. Now, you might also see another option is the right endpoint. Okay, well, what is that? It says, look, if you have an interval, choose the right-hand side. And, okay, then whatever the height is at the right-hand side, that's what you pick. And that gives you your area. All right, well, of course, what are some other options? You could pick midpoint. What does that say? Well, it says just go halfway in between. So if that's our interval, then we go halfway in between. And then that's our height. All right, great. And what else can you do? Well, you could say, look, I want to make sure I get a lower bound or get an upper bound. So if I want a lower bound for the total, I just have to lower bound each little rectangle. And so if I want a lower bound, that says find the min. And now, where is it? Well, it might be at the left or right. It often is. Or it might be somewhere in between. You just have to find it. Now, in general, if you're looking for min or max, it's very inefficient. Because what you have to do is you have to optimize each little individual one. Whereas if you say, look, I don't care which point I use, because in the limit, yeah, there is a limit involved, it really won't matter. So here is a case where the max happens at the right endpoint. The left endpoint. It can vary. So there you go. You just have to have a rule for how to pick, and you can pick almost arbitrarily. You can even vary the rule. The only important thing is that for each interval, you pick a point. And in the end, it won't matter which point you pick as long as your function is nice. All right, so now we can do Riemann sum. So if you ever see a question, okay, use a Riemann sum or find the Riemann sum, the procedure is break it up into the right number of intervals, make sure you know the width of each interval because that's going to show up in your Riemann sum, and then for each interval, find the right height because that's going to be height times width is the area of the contribution of that piece. And the height will be based off of what rule do you have for choosing the point to plug in. Put it all together, life is good. Yeah, of course, life is wonderful. Well, now we need to talk about something important, which is notation. And I know what you're thinking, oh, mathematicians and their notation, come on. Do you really have to do that? And the answer is, yeah, we do have to do it because it's very important to have good notation. You see, good notation allows us to express things in a simple, concrete manner, and we want things to be simple. We don't introduce notation to make things hard or to obfuscate. We introduce notation to say, oh, let's sort of condense into some nice compact form. So it makes it easier to work with. You can imagine how hard it would be to do algebra homework where you weren't allowed to use any mathematical equations. You had to write everything out longhand. And now, that's how they did it. If you go back hundreds of years ago, everything was written out longhand. And it was very frustrating. And so notation, it made things so much easier to work with and allowed us to make progress on solving much harder problems. And we like being able to solve harder problems. So, what are we after when we talk about notation now? Well, we're adding lots of little pieces together. And what we'd like to do is find a way to just say, okay, here's sort of what it means to add lots of little things together, which are also closely related to one another. So, we're going to introduce notation for sums. All right, so what do we have? The way we would read this part says that the sum from P to Q, and K is an index here, A sub K is really A sub P plus A sub P plus 1 plus A sub P plus 2 plus plus A sub Q. The punchline, by the way, for our notation, it's actually down here, says, hey, we'd like to have a nice way to talk about the ... And whenever you see the ... it's shorthand for, and the pattern continues. So we'd like to say, okay, well, let's just write down that pattern in a nice form. So what do all the symbols represent? Where do they come from? Well, the first symbol to talk about is this capital sigma. So why use that? Well, sigma, think of it as it starts with S, and S is for sum. So you can channel your inner Cookie Monster. S is for sum, that's what it means to me. S is for sum, that's what it means to me. S is for sum, that's what it means to me. Sum, yes, it's sum. All right. Well, anyway, something like that. Okay, so that's why we see the sigma. It's really a stand-in for saying, hey, we're adding things together. So whenever you see sigma going forward, think sum. Now, you have an index, and you'll notice it's not here on this right-hand side. There's no k. See, what happens is that k is varying, and we just have to say, where do you start, where do you stop? So we have to specify. So we say start at p, so which where you start, stop at q. So we put our start at the bottom, stop at the top. So you'll notice, see, we start a sub p, that's our first term. Then after p, we go up by 1, p plus 1, then up by 1 again, p plus 2. And we keep going until we get to q. So the k is our indexes, and it ranges from p to q. All right, now what is it when we say a sub k? Well, a sub k is the pattern that we have. What do the terms look like? And we think of it in terms of k. So in other words, if you give us a value of k, it'll say, hey, this is what it's going to look like when it comes back out. So that's what our notation is. So this just allows us to say, ooh, there's a nice way to rewrite our sum in very simple format. Now, a couple of basic properties. And the first thing should really come as no surprise, which is sums work really well with addition and pulling out constant factors. You're like, wow, we've heard that before, haven't we? Things like derivatives work really well with sums and pulling out factors. And also, I guess, the antiderivatives. That's something we talked about recently. So the moral is, look, if I have a sum and there's an addition, I can break it up. If there's something which doesn't depend on the index, so it's a constant, it can be pulled outside. So this is another way of saying, there's a very fancy word, we've mentioned it before, that says, hey, this is linear. But of course, we talk about things like adding. Yeah, adding is linear. No surprise. No surprise. Now, the other basic property we should mention, and we won't rely on it too much, but it's nice to mention it now, so we can get it sort of in the back of our heads for in the future when we will need it. It says, suppose we add, we're going to start at p plus r, go to q plus r, but we have a sub k minus r. Now, what's the first term? Well, what would it be? Well, you say, okay, k is p plus r, right? So you'd have p plus r minus r. P would be the first term. And you keep going, what's the last term? Well, it'd be q plus r minus r, q. So it's really the same as starting at p and going to q of this new index a sub l. So this is something, I like to think of this as reindexing, but you can also think of this, there's another sort of idea, as some sort of what we might call a substitution. Now, that sounds like a strange word, but what are we really doing? It says, hey, let's introduce some new index. And what's the rule? Well, the rule will be the following. I'm going to say, I'm going to let k here, k is p plus r. So what I'm going to do is I'm going to say, well, let's let k be equal to, well, let's see. I want to make sure we get this right. We'll make it L plus R. And so there's there's this direct relationship. So what corresponds to p plus r here corresponds to p there. And so you can use this, and now what happens? Well, everywhere where you see k in this expression here, replace it by L, and you get that expression there. Now you might say, well, how does that work? Well, notice things like, what do we have? Well, we'll have the sum. Now here you have k, so that's really L plus R equals P plus R, right? Because I'm just replacing k by L plus R. You might say, well, hey, haha, Steve, you're stuck. There's no k there. There's actually kind of a k, but we obfuscate it because it's kind of redundant. That's two kind ofs in one sentence. So yeah, that is being kind of vague. So when we don't write down this is attached to a variable, it's because we understand what the variable is by context. But we really know that, look, this really means we're going from k is p plus r to k is q plus r. So we say, oh, well, that's really L plus r equals q plus r. And now you have a L plus r minus r. So what you've done is everywhere you saw a k, you put an L plus r. And then if you simplify, you say, wow, look, the r's, they cancel. And then you get the following. That's the sum from L equals P up to L equals Q. And I'll just suppress the L equals notation of A sub L. So that's what happened there. It was a reindexing, or what you might call a substitution, where we substitute one index for another. Now, there's a couple of sums which we're going to mention. And, well, if we add 1 up, okay, it's probably not too hard to add 1. 1 plus 1 plus 1 plus 1 plus 1 plus 1. That's like the first way that people learned to count, right? We said, okay, just add 1, 1, 1, 1, 1. And how many times? Well, you started at 1, you stopped at n. So you added up 1 n times. So the result is n. Great. Beautiful. Nice. Okay. Well, a little bit more interesting. What if we add up the value of k? So in other words, we had 1 plus 2 plus 3, and we kept going all the way up to n. Not so easy now, is it? Okay, but now here's a fun little trick. We're just going to write it backwards. Now you might say, well, yeah, sure, write it backwards. No problem. But it's still adding the same numbers together, Steve. How does that help? I mean, where's the advantage? Well, now, look, this is what we want. It's also this is what we want. It's just the same numbers, just in a different order. Well, let's add them together. Term by term. 1 plus n plus 1. 2 plus n minus 1. Oh, that's n plus 1. 3 plus n minus 2. Oh, that's n plus 1. And all the way here, n and 1, well, that's n plus 1. Oh, wow. When we add them together, that way, it's n plus 1 plus n plus 1 plus n plus 1. And there's a total of n terms. And so we say, okay, so that's really, there's n of these. Each one is n plus 1. So that's n times n plus 1. But remember, we added it twice. So it's twice what we want. So if we think of these as our individual sums, we say, oh, this is twice the sum we want. And therefore, we get n times n plus 1 over 2. All right. K squared, a little bit more difficult. It can be done, but we'll just accept that that's the formula, and there's ways to prove it. I will mention this one is really cool. The sum of r to the k. Well, what do you have? All right, let's call, whatever the answer is, we'll call it t. So you have, if you start here at 1, you get r, all right, because you get r to the 1, then you get r to the 2, and you keep going all the way up to r to the n. Now, multiply by r. Well, r times r is r squared. R squared times r would be r cubed, and so forth and so on. And you'd get an r to the n, that's from the previous term, and then you get r to the n plus 1. So it's still powers of r, except now you start at 2, and you end at n plus 1. Oh. Notice how most of the middle matches up. Well, that's great. Whenever you have lots of things matching up, it says, hey, we should be thinking about ways to combine to get cancellation. And in particular, we'll do the following. We're going to subtract the first one, add the second one. And if you do that, well, you'll get here r times t minus t, which is r minus 1 times t. And then all these terms cancel. Gone, 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 gone. Except the last term doesn't have a part to cancel with. And that's the one that's being added, r to the n plus 1. And the first term didn't have something to cancel with, and that's being subtracted, minus r. And therefore, divide, and you see, aha, you get r to the power n plus 1 minus r divided by r minus 1. And that's beautiful. This, by the way, is called geometric. Geometric here just means you multiply. So whenever you hear something that says, oh, there's a geometric thing going on here, it means a multiplication was happening. So there's our ideas. Break things up into small parts, each part being a rectangle, right? We're thinking Riemann sums. Add them together. That's a great approximation to our answer. Smaller parts, better approximation. And we see where this is going. And smaller and smaller and smaller. And of course, now we have good notation. We know how to write sums using this notation with the sigma. Where do you start? Where do you stop? And what does each term look like? And that gives us a way to compress. And of course, we can also decompress. And now we're ready to start looking. What is the total? What is it? How much is there? Well, let's go and do some practice. See you soon.